Okay. So good morning, students. Welcome to the Real Analysis live lectures. So in yesterday session, we have discussed about isometry and homeomorphism. Today we are going to see space of continuous functions. Space of continuous functions. This is lecture 23, no? Okay, can you hear me?
Yes, ma'am.
Yes, ma'am.
Just a minute. Okay. So what is space of continuous function? We will define it. Let MD be a metric space. Let MD be a metric space and let C of M, which is equal to set of all functions f from M to R, real valued functions defined from M to R, where f is continuous. F is continuous. Define for any f comma g belongs to C of M. F plus g of x is nothing but f of x plus g of x, and alpha times f of x is equal to alpha times f of x, where alpha is a scalar, where alpha belongs to R, scalar, real number. Then we know that, then we can easily prove that this C of M is a vector space. What is a vector space? Everybody know a vector space from linear algebra? Linear space or vector space? So if MD is any metric space, we denote C of M. What is C of M? It is collection of all continuous functions from M to R, real valued functions. Okay, and we define its vector addition and scalar multiplication in the following manner, in this manner, like f plus g of x is nothing but f of x plus g of x, and scalar multiplication is defined like this: alpha times f of x is nothing but alpha f of x. Okay, this will form a vector space. We will have a theorem. If f comma g from M to R are continuous, then f plus or minus g, f into g, then f by g, alpha times f, minimum of f comma g, and maximum of f comma g, these are also continuous, are also continuous. Okay, we can easily prove that if f and g are continuous functions from metric space to R, then their addition, subtraction, multiplication, division, also scalar multiplication, and minimum of two continuous functions, maximum of two continuous functions, that will be again a continuous function. Okay, we can easily prove this. So how we will prove this? F and G are given to be continuous. Okay, I will prove. Just you have to take x, start with a sequence xn, convergent sequence you take, and since f is let xn be a sequence, xn be a sequence in M such that xn converges to x. So start with a convergent sequence, and since f is continuous, now function f and g are given to be continuous. So what can I say about f of xn and g of xn? F is continuous. What this will imply? F of xn will converge to f of x, right? And since g is also continuous, g is continuous, what can I say? G of xn will converge to g of x, right?
Yes, ma'am.
So now addition, if we are having xn converges to x, yn converges to y, then what we know about xn plus yn? It will converge to x plus y. So f of xn plus g of xn will converge to where? F of x plus g of x, right? So this implies
Yes, ma'am.
f plus g of xn converges to f plus g of x. So what this gives? This implies f plus g is continuous function. Is that right?
Yes, ma'am.
Similarly, for negation, product, addition, subtract, division, all things you can represent in terms of addition, subtraction, okay, and like that you can prove. Okay, so this will be an easy exercise. Prove this. Okay, minus, similarly you can prove, product you can prove, then division, alpha times f, alpha is a scalar, okay, minimum of f comma g and maximum of f comma g, they are also continuous. You need to write all functions in terms of addition, subtraction, and use these results. Okay, think on this and try to prove this. Okay, similarly prove remaining. Okay, so now we will go to connectedness. So definition, let MD be a metric space. And a metric space is said to be disconnect, then MD is said to be disconnected if there exist non-empty disjoint open sets A and B such that M is equal to A union B. That is what? There exists non-empty, A is non-empty, A is not equal to 5, B is also non-empty. I might have written reverse. Okay. There exists non-empty, B non-empty set, and A and B are open sets. Okay, so where what is, they are disjoint also, so A intersection B is equal to empty set and M is equal to A union B, where A is open and B is also open. Is that right?
Yes, ma'am.
Then that metric space is said to be disconnected. Otherwise, if it is said to be connected. Okay. The pair, such a pair, the pair A comma B is called disconnection or separation. Disconnection or separation of M. Separation of metric space M or metric space MD. Okay. If there is no separation, if there is no separation of M, then M is called connected space, connected metric space. Is that okay? Connected and disconnected. When we say that connected, if there does not exist two non-empty disjoint open sets such that M is equal to A union B. Okay. If there exists, that metric space is said to be disconnected. For example, let MD be a discrete metric space. Discrete metric space with at least two elements. At least two elements. Then MD is disconnected. So MD be a discrete metric space with at least two elements. So how we can prove that it is disconnected? If we can find A and B, two non-empty disjoint open sets such that M is equal to A union B. So how we can write that set? Let X belongs to M. Then M can be written as singleton X union M minus X, right? If I take any element from M, then M can be written as singleton X union M minus X.
Yes, ma'am.
How many elements are in M, that doesn't matter. Okay. And what we know about every subset of discrete metric space? What we know about every
Okay.
subset of discrete metric space? Which are disjoint as well as open? Why they are open sets? Every subset of a discrete metric space is open. We have already proved. Can you recall this? Discrete metric space are open. Every subset of a discrete metric space is open. We have already proved. Can you remember this? So singleton X is open in discrete metric space as well as its complement is also open, and the same can be written as singleton X union its complement, right? So, and which are automatically disjoint.
Yes, ma'am.
Therefore, this is a separation. Therefore, M is, which implies M is disconnected. Okay. Now we define Clopan set. A set which is both open and closed, which is both open and closed is called Clopan set. Clopan, closed as well as open. Clopan set. Okay. So, what are the examples of Clopan sets? Empty set is open as well as closed. Whole space. Clopan sets. Right? Is that okay?
Example.
Ma'am,
Yes.
सिंगलटन सेट क्लोपन असते का?
Singleton set Clopan असतं का?
हा?
It depends on a space. Which space you are talking about? Suppose if you take discrete metric space, what do you know about it? Every subset is open.
Yes, ma'am.
So if just now we have here, these are Clopan sets. The singleton set X is open. The singleton set we are saying open, right? In discrete metric space, and its complement is also open. Can you see this?
Yes. Yes.
So since its complement is open, it is closed also. Right? This singleton X and M minus X, they are a complement of each other.
Yes, ma'am.
Yeah, and both are open means other one should be closed because one is a complement of other. So this singleton X and M minus
Okay, ma'am.
singleton X in discrete metric space, these are Clopan sets, open as well as closed. Is that okay?
म्हणजे मॅम एक सेट जर
Yes.
म्हणजे एक सेट जर ओपन असेल तर त्याचा कॉम्प्लिमेंट हा क्लोज असतो असं का?
ओपन असेल तर त्याचं एक, इफ A is open then its complement, A complement must be closed ना.
ओके, हो मॅम, बरोबर.
So that's why I am taking it. So it depends on a space which if it is R with usual metric, then singleton set is not open. Okay, singleton sets are closed. So they are not Clopan sets in R with usual metric space. If it is R with discrete metric space, then it is Clopan. So it depends on a set in which metric space we are talking about. Is that okay?
Yes, ma'am.
Now we'll have a theorem. M is connected if and only if M contains no non-trivial Clopan sets. No non-trivial Clopan sets. Trivial Clopan sets कोणते आहेत? Which are trivial Clopan sets?
Pi and whole space.
Pi and whole space. These are trivial Clopan sets. Other than that, if there is a set which is open as well as closed, then we will call it as non-trivial Clopan set. And if in a metric space there exists non-trivial Clopan set, then it will be disconnected. If there does not exist non-trivial Clopan set, then it will be connected. That we want to prove now. Prove. Assume that M is connected, or suppose M is connected. And on the contrary, what we want to prove now? We want to prove M contains no non-trivial Clopan sets. So on the contrary, assume M has non-trivial Clopan sets. M has a non-trivial Clopan set, say A. So we are assuming M has non-trivial Clopan set, means we should get somewhere contradiction, okay? So that is non-trivial Clopan sets. A is non-empty, A is not equal to whole space M, and A is open as well as closed, open and closed. Is that okay? It is a Clopan set, means it is open, closed. They are non-empty also. Means non-trivial means it is not empty, not whole space M. Is that okay? So what this, if A is open, what I know, A is open, A and what can I say about A and A complement? Open, and M can be written as A union A complement, right? A is open, so A is closed also. Since it is closed, A complement will be open. So A and A complement will be open. But M can be written as A union A complement, right? Is that
Yes,
okay?
ma'am.
Which is what way it gives? It is separation. It forms a separation, means M is not disconnected, which is, we can say, which is contradiction, which is contradiction. Therefore, there must not exist a non-trivial Clopan set. Okay. Now conversely, therefore M has no non-trivial Clopan set. Now conversely, Conversely, assume M has no non-trivial Clopan set. And what we want to prove? M is connected. So on the contrary, again assume M is disconnected. Okay, assume M is disconnected. If it is disconnected, then what will happen? Then there exists A, B open sets such that M is equal to A union B, A intersection B is non-empty, disjoint, right? And A is also non-empty and B is also, or we can write here only, okay. There exists A non-empty, B non-empty open sets such that M is equal to A union B and A intersection B is non-empty, right? Now since what is A complement? What is A complement from these two? A union B is nothing but M and A intersection B is empty. What is A complement?
B.
It
M
is
minus
B.
A.
B.
Yes, B. What this implies? A complement is open. This implies A must be closed. B is open, na? B is open, so A complement is open. Therefore, A is closed. But already we are started with A is open set. So we are having non-trivial Clopan sets. Therefore, A is non-trivial Clopan set. Therefore, there is A, or this implies A is non-trivial Clopan set, and which is contradiction. Therefore, what? Our assumption is wrong. What is our assumption? M is disconnected is wrong, means therefore M must be connected. M is connected. Is that okay?
Yes, ma'am.
Now, lemma. Let E be subset of metric space M if U and V are disjoint open sets, in E, then there are disjoint open sets A and B in M such that U is equal to A intersection E and V is equal to B intersection E, that we want to show. What is given? E is any subset of a metric space M. M is a metric space, E is a subset of. And what is U and V? U and V are disjoint open sets in E. Then we want to show there exist disjoint open sets A and B in M such that U is equal to A intersection E and V is equal to B intersection E. So how can I prove this? What is given? U is open. Since U is open, what can I say by definition? For every x in U, there exists an open ball which is totally contained in U, right?
Yes, sir.
Since U is open, for every x in U, there exists epsilon radius, we can say there exists epsilon x. For this x, there exists one radius, epsilon greater than 0, such that b epsilon x, which is totally contained in U. So what this implies? E intersection b epsilon x also contained in U. Can I say this?
Yes, ma'am.
You can have like this. M is a whole metric space. M is this is a metric space M. E is any subset in M. U and V are disjoint open sets in E. This is say E. U and V are disjoint open sets. Say this is U, this is V. Okay. They are disjoint open sets in E. Then what we want to show? There are disjoint open sets A and B in M, such that U is equal to A intersection E. Are you getting this? U is equal to A intersection E and V is equal to B intersection E. So if B epsilon x is contained in U, B epsilon of x is contained in U, then E intersection B epsilon of x is also contained in U. Is that right?
Yes, ma'am.
Now similarly, about same thing we can say for V also. Similarly, since V is open in E, for every x in V, now instead of x we will write every y in V, there exists some delta greater than 0 such that B delta depending on y is contained in V, right? So this implies E intersection B delta y of y is also contained in V. Now what is U intersection V? They are disjoint. U and V are open sets, they are disjoint. Since U intersection V is empty, what this implies? E intersection B epsilon x and intersection B delta y,
Fine.
it must be empty, right? In particular we have B epsilon x by 2 intersection B delta y by 2 of y is also empty for every x in U and for every y in V, right?
Yeah.
E intersection this is empty. Now I am taking half of radius of epsilon and delta. So their intersection must be also empty.
Yes, ma'am.
Let me write like this. Yes. Now let A is equal to union of these all balls epsilon x by 2 such that x belongs to U. Take their unions and say B is equal to all open balls of radius delta y by 2 centered at y where y belongs to V. Then what can I say about A and B? What can I say about A intersection B?
Fine.
It must be also
Empty.
empty.
Why?
And what is A intersection A? It is E intersection union x belongs to U such that B epsilon x by 2 of x, right, which I can write as union or x belongs to U. This is union symbol. X belongs to U such that B epsilon x by 2 of x intersection E. I can write like this. Can I write like this?
Yes, ma'am.
So E intersection A is nothing but U. Union X belongs to U. Right?
Yes, ma'am.
Therefore, E intersection A is nothing but U. And similarly, we can get E intersection B is nothing but V. Is that okay?
Please repeat the last step.
E intersection, what is E intersection A? What is E intersection A? A is nothing but this I am taking union of all these balls of radius epsilon by 2. Okay. For each x I am having one epsilon. I am just saying it is epsilon x because x, if I change x, epsilon will change. So epsilon x I am saying. Is that okay? Like this.
Yes.
Let me draw here. Suppose this is your U. Suppose this is your U. For each x, I am having one ball. Open ball. Is that right? This is epsilon x, epsilon, another epsilon, whatever may be radius. For each x, I am having one ball, open ball, which is totally contained in U. I am taking all union of that balls. And anyhow, this is contained in E. This is my E. E, where is E? You can see here. See here. Is this E? This is my E.
Yeah, ma'am.
आणि याचे प्रत्येक x साठी there is a ball I am taking. Let me take other. For every x I am having one ball. Right? So what is E intersection union of these balls? It is U itself.
Yes, ma'am.
Yes, similarly intersection union of balls of this. This is nothing but V. Okay, this is my this ball is nothing but my u. This is ball is nothing but my v. I will change this.
Got it.
Is that okay?
Yes, ma'am.
Okay, so disconnected, and that we will tomorrow we will take that one. So there are some connected theorems. Okay, so this much is enough for today. Tomorrow not, Monday. Monday also there are lectures, na? So Tuesday.